So let's go ahead and look at this first warm-up problem. So I'm going to rewrite it in our long division kind of notation so that it's easier to work with. So we've got x minus 4 is dividing into 5x cubed plus 2x squared plus x minus 4. Okay, so let's see. We want to think about the x term as being like the leading term of the divisor, and the 5x cubed term as being like the leading term of the dividend. So we want to think, what can we multiply this x by to get 5x cubed? And so that's going to be 5x squared. So now notice if we do that, we get 5x squared times this whole thing. So we're going to have to distribute it. We'll get 5x cubed. So that's from multiplying 5x squared to x. And then we'll have minus 20x squared. Again, by distributing this 5x squared onto the minus 4. Now we want to go ahead and, yes.
Can you re-explain how you got the 5x squared?
Yeah, because we want the whole term right here, which is just plain old x, so that we achieve the leading term of this dividend, which is this 5x cubed. So by comparing the coefficients, we know that the coefficient here is 1, the coefficient here is 5, so we need to multiply by 5. And then by comparing the exponents of x, here we have x to the 1, here we have x cubed, so that means we need an additional x squared. Okay, so and then you have to distribute onto all parts of the divisor, so we distributed it onto this term and this term, which gave us this minus 20x squared. Now maybe think about this minus sign coming through, so that's going to give us a minus 5x cubed there and a plus 20x there. Now we can just subtract straight down, not even worrying about it. So 5x cubed minus 5x cubed, so that cancels, which is exactly what we wanted to do. 20x squared plus 2x squared is going to be 22x squared. So that's kind of like our intermediate remainder or something. So what we can do now is bring down this part. So bringing that down, we have plus x minus 4. And now we play the same game again. So we think, what do I need to multiply to x again here to achieve 22x squared? So my coefficient here is 1, my coefficient here is 22, so that means I know that I need to multiply by 22. My power of x here is x to the first. My power of x here is x to the second. So that means I need to multiply by an additional x to the first. That's because x times x is x squared. Okay, now we go ahead and take this 22x and distribute it onto both of those terms. So that's going to give us 22x squared from the first bit, and then minus 88x. So that's because 22x times 4, that's 88x, and then we've got this minus sign built in, and then we do the same thing that we did before, so we group and subtract. Just like long division of numbers. But now maybe we distribute this minus sign through, so that's going to change the sign of both of those. Now we do 22 minus 22, so that's 0, and then we have x plus 88x, that's going to be 89x, and then finally minus 4, that's from bringing this minus 4 down. Now we've got one last step, because remember we stop when the degree of this is smaller than the degree of this. Notice the degree of this is 1, the degree of this is 1, so those are equal. That means we can do one more step. So what we'll do is think, what can I multiply to x to get 89x? So that's going to be 89. So plus 89. So now 89 times x, well, that's 89x. That's the whole goal. And then 89 times negative 4, well, let's see what that is. 89 times negative 4, well, let's see. 90 times 4 is 360. So it's going to be 356. So it's going to be negative 356. And now we group and subtract. So let's group and then subtract. We can take this minus sign and distribute it through to both of these. That gives us that. We've got 89x minus 89x. Those are going to cancel. Then we've got negative 4 plus 356. That's going to give us 352. And that'll be our remainder because the degree down here is 0, which is smaller than the degree up here. So maybe we would finish this off by saying remainder 352. So we've got, this is the quotient, this 5x squared plus 22x plus 89. And then the remainder is this 352. That's it. I had a weird intonation on that, but the remainder is 352. Okay. So let's maybe do one more. And then we'll move into what we're doing next, which is factoring, which will allow us to solve equations involving these polynomials instead of, you know, just linear types of equations. So that's going to be good. Okay, so let's maybe say this one is next. So 2x squared minus 4x plus 1. So that's the dividend, and then we're going to divide that by 3x plus 2. So that's the divisor. So that's a second warm up. So I'll give you guys, I don't know, like 2 or 3 minutes to work on that, and then we'll go through this one as well, and then move on to what we're doing for the day. Practice, this one is going to be like a little bit trickier because you're going to have fractions as part of the quotients. But as long as you like keep all the bookkeeping in track, it's essentially the same as this previous example. So I'm going to write it the same kind of way with our long division setup. So we've got 3x plus 2 is dividing into 2x squared minus 4x plus 1. Something like that. Now we want to play the same game. So look at the leading coefficient here, which is 3x. I should say the leading term. And then the leading term here, which is 2x squared. And we want to think, well, what do I multiply to 3x to turn it into 2x squared? So I know that I need an x because I've got a single power of x here and I've got an x squared there. That's going to bring me up to x squared. But now I need to multiply something into 3 to turn it into 2. And the easiest way to do that is to multiply by 2/3. So notice putting that 3 in the denominator is going to cancel the 3, and then putting the 2 in the numerator is going to essentially turn it into a 2. Okay, so now what we want to do is take this 2/3 x and distribute it onto both of these terms. So here, 2/3 x times 3x, that's going to be 2x squared. Those are always going to be the same. Otherwise, we've made like a mistake. I mean, the setup is that we should always get those two to be the same at every step. These leftmost guys should be the same. Okay, and now we do 2/3 x times 2. Keeping in mind that like 2 is 2 over 1, and when you multiply fractions, you just multiply straight across. So that's going to give us plus 4/3 x. So we've got something like that. Now we're going to group and subtract. So let's group this and subtract. That means we need to distribute this minus sign through to both of these terms. So we're going to have 2x squared minus 2x squared. So that is going to cancel, which is always the goal. And then we have negative 4x minus 4/3 x. So I don't know, you don't have to do this over to the side, but if you want to, you can do this over to the side. Notice we're doing minus 4x minus 4 over 3x, which means we need to find a common denominator and stuff like that. So the common denominator is going to be 3. We can think about that 4 as 4 over 1. So if we build up the denominator, that would involve multiplying the numerator and the denominator by 3. So that's going to give us negative 12 over 3x minus 4 over 3x. So that's going to be negative 16 over 3x. So that's what we get from this column. So here we have minus 16 over 3x plus 1. So then bringing the 1 down. Okay, great. Now we're going to play the same game again. So we need to think about what do we multiply to 3x to turn it into negative 16 over 3. So the 3 needs to move from the numerator to the denominator. So that means we're going to need a 9 in the denominator. Because notice 3 over 9 will give us a 3 in the denominator. 3 over 9 is the same thing as 1 over 3. And then we need a 16 in the numerator. So we've got a 16 up there. And then we need it to be negative. And then the power of x is the same. Notice we've got 3x to the 1. And then this is also something times x to the 1. All right. So now let's see what we get. So negative 16 over 9 times 3 is going to be negative 16 over 3x. Remember, that's the goal. And then negative 16 over 9 times 2, so that's going to be negative 32 over 9. So 16 times 2 is 32. So notice when we did this first multiplication, we used the fact that the denominator simplified or whatever. Okay, so now we're going to do grouping and canceling. So, sorry, grouping, subtracting. So we can distribute this minus sign through. That's going to change the sign on both of those from minuses to pluses. We've got minus 16 over 3 times x plus 16 over 3 times x. So that's going to cancel. Then we've got 1 plus 32 over 9. Now you can do this on the side if you want, but I'm just going to do it right here. I'm going to go ahead and think about this 1 as 9 over 9. So maybe I'll like scratch that 1 out and just think of it as 9 over 9. That's the same thing. So we have 9 over 9 plus 32 over 9. That's going to be 41 over 9. Now we've achieved the remainder because the degree here is 0. The degree here is 1. That's smaller than, so 0 is smaller than 1. So we have a remainder. So 41 over 9. So there's our solution. Our quotient is this 2/3 minus 16 over 9. Sorry, 2/3 x minus 16 over 9. And our remainder is 41 over 9. Okay. So I think those are good ones to keep in mind. Now let's move on to factoring. So let's see. Yeah, okay. So we're going to do factoring in a couple of different stages. So the first stage will be taking out a common divisor. And then the second stage will be like common factoring formulas. And then the third stage will be like more general factoring. So let's look at maybe stage 1 first. So factoring. So like I said, stage 1. So common factors. So the idea is that we want to reverse the multiplication. So if we have something like 3x squared times x minus 4. So if we were to multiply that out using the distributive rule, we would have to hit both terms with 3x squared. That'll give us 3x cubed minus 12x squared. And so our first goal is to do simple factoring like that in reverse. So we want to start over there with the 3x cubed minus 12x squared and factor it into this thing right here. So take out a greatest common factor. So notice 3x squared is a greatest common factor of each of these. So, and you can do this just by looking at what exponents you have. So the greatest common factor is always going to be the smallest possible exponent you have for each variable. And then after that, it's just the greatest common divisor of the numbers or whatever. So here, notice here we've got an x squared. That's the lowest power of x. That means we can factor the x squared out of the whole thing. And then the greatest common divisor of 12 and 3 is 3. So that means we can divide out a 3. Okay, so let's maybe look at an example. So let's say we have 2x to the fourth minus 16x squared plus maybe 16x cubed, and then finally plus 8x squared. So let's see how we can factor this. So I'll put a parentheses here. Now let's look at each term. So let's look at the variables first. I've got an x to the fourth, an x cubed, and an x squared. So since x squared is really a factor of each of these, given that x cubed is like x times x squared, and x to the fourth is like x squared times x squared, that means I can factor an x squared out of this whole thing. And like we set up here, this is like the same thing as having the smallest power of the variable. So notice the smallest power of x that's available here is x squared. Now we look at the coefficients. So we've got 2, 16, and 8. And we look at just the standard greatest common divisor. Yeah, the greatest common divisor, or highest common factor, sometimes it's called, of those 3 numbers. So that would be 2. So 2 divides 2, 2 divides 16, and then 8 is divisible by 2 also. So that means we can factor a 2 out of the whole thing as well. And then from there, we just kind of eyeball it and say, okay, well, if I have 2x squared here, what do I need in order to get 2x to the fourth? Well, I need an x squared. That's because if I were to distribute this through, I would get 2x to the fourth. And then I just work myself to the right. So 2x squared, what do I need to get? Minus 16x cubed. So that's going to be minus 8x. So notice if I were to distribute that through, I'd get 2 times negative 8 is negative 16. X squared times x is x cubed. And then the same kind of thing here, but I'll just have plus 4. For the same reason, 2 times 4 is 8. And then we just have x squared by itself over here. Okay, so that would be like taking out a greatest common factor with one of these. Okay, well, maybe let's look at another example. So let's look at maybe minus 3 over 5 z cubed minus 6z squared. Okay, so there's a couple of different things that you can do here before you get started. You could just take out like a z squared. Notice that's a common factor of each one because this is z cubed, and call it done. And that would like completely be the correct answer. But if we want to make this as simple as we can get it, maybe our best bet would be first to combine this with a common denominator. So let's see how we can combine this with a common denominator. So notice if I've got a 5 here as the denominator, and I have a 1 here as the denominator, that means my common denominator will be 5. So I can build the second term until it has a denominator of 5 by multiplying by 5 over 5. So let's see what that gives us. That gives us negative 3 over 5 z cubed minus 30 over 5 z squared. Good. So now we've got a common denominator, so maybe we can put this together into minus 3 z cubed minus 30 z squared all over 5. So we just combined it together all into the same common denominator. But now notice that we have a common factor in the numerator. Each term is divisible by z squared because here we have z cubed and z squared. So z squared is the lowest power of z we see. And then 3 divides into both of these evenly. So maybe we'd want to divide out a 3z squared, but then also we've got minus signs everywhere. Maybe we could divide out a minus sign as well. So we could do minus 3z squared And then what are we going to be left with? So here we're going to be left with z plus 10 over 5. So now let's talk our way through that. So notice if we were to distribute this minus 3z squared onto z, we would get minus 3z cubed. And we distribute it onto 10, we get minus 30z squared. So we've got it. So again, like there's not only one way to factor these things out, but maybe there's a preferred way. And I would say maybe the preferred way in this example is a little less clear, but this is most definitely one nice way of factoring this into simpler terms. Okay, so next, I want to talk about some common factoring formulas, and then we'll look at some examples associated with these common factoring formulas. And so these are going to be built off of something that we've seen whenever we were multiplying out polynomials. So let's look at that. So common factoring. Formulas. Okay, so the first one I want to go over is this a squared plus 2ab plus b squared equals a plus b quantity squared. So notice that's like a common multiplication of two polynomials that we had seen before, but now we're just writing it in a different order. So that's how this would factor. If you see something that looks like this, then you can factor it like a plus b squared. And now we're going to have a similar one with a minus sign. So a squared minus 2ab plus b squared. So that's going to be a minus b squared. Again, that's one that we've seen before, just written in reverse. Then this next one is also one we've seen before, just written in reverse, and that's a squared minus b squared is a minus b times a plus b. The so-called difference of squares formula. And then here are two new ones, which I think we saw when we were doing examples of multiplying polynomials, but we didn't really stress it too much. And these don't show up as often, but it's always good to kind of keep in mind that they exist. So they're the sum of two cubes and the difference of two cubes. So a cubed plus b cubed equals, so you can factor that as a plus b, and then a squared minus ab plus b squared. Good. And then likewise, we can have a cubed minus b cubed. So that'll be a minus b, and then a squared plus ab plus b squared. Okay, so let's look at some examples using these common factoring formulas. Okay, so maybe for our first example, we'll look at this. So 18x squared minus 48x, and then plus 32. Okay, so the first thing that we'd always want to do is look for a greatest common factor before we get started. And so we want to look at all of these terms and say, is there a common factor for them? And in this case, there is, and it's 2. 2 is the common factor for each of these. Notice there's no power of x that's a common factor because this guy over here does not have an x attached to it. But they're all even, which means I can factor a 2 out. So now if I factor a 2 out, what are we going to get? Well, we're going to get 18 divided by 2, that's 9x squared. I'll get minus 48, so that's minus 24x. Sorry, I should say minus 48 divided by 2. And then I have 16 because that's 32 divided by 2, so plus 16. And now we want to think about factoring it. So at the moment, we're just talking about these common factoring formulas. So does this look like one of those maybe? And yeah, it kind of looks like this one right here. So, but what are the values of A and B if we have something like that? Well, notice that 9 is equal to 3 squared and 16 is equal to 4 squared. So maybe we could think of this like with the following shape. So this is 2, and then we have 3x squared, and then over here we have 4 squared. And now we just want to check in the middle, do we have 2 times 4 times 3x? But we do, because 2 times 4 times 3x is most definitely 24. 2 times 4 is 8 times 3 is 24. So we do, this works out. So like I said, we have this formula right here with A equals 3x and B equals -4. Sorry, maybe B equals just 4. But that tells us that this factor's like, well, we have this 2 that comes out front, and then we have 3x minus 4 quantity squared, like that. And then if you wanted to, we could check that just by doing the multiplication in reverse. So we'll have 2 times 3x minus 4 times 3x minus 4. And then we want to do all the foiling, so we do this multiplication here. And we would see that we would get 2 and then 9x squared minus 12x minus 12x plus 16. But then that pretty quickly goes up to what we started at. So it's okay. Okay, good. So let's maybe do a couple more of these special factoring formulas. And then we'll move on to like more general factoring maybe. Okay, so I want to maybe leave up those common factoring formulas, so I'm gonna go ahead and erase this. All right, so let's see, another one, maybe 81 minus 16y to the 4th. Okay. So notice that we don't have anything to the 4th power over there, but we can think that something to the 4th power is the same thing as squaring something that's already squared. So maybe we can actually make this fit into one of those shapes over there. And we can, if we notice that 81 is 9 squared, and then 16y squared is 16y to the 4th is the same thing as 4y squared, all squared. So let's just check to make sure this makes sense. So 9 times 9 is 81, so we're good to go there. And then 4y squared times 4y squared, well, the 4 times 4 is 16. And then the y squared times y squared is y to the 4th, using exponent rules. So yeah, this is true. This is an okay way to write that. But now we can apply this difference of squares formula right here, where a is equal to 3 and b is equal to 4y squared. So that means this thing is going to factor, sorry, I shouldn't say 3, I meant 9. I got ahead of myself a little bit. 9 minus 4y squared, and then 9 plus 4y squared. And now, I mean, we could like pat ourselves on the back and say, okay, job done. But it turns out that we can do this again, because this thing right here is also of that form with just different choices of a and b. Notice we can write this as 3 squared minus 2y, the whole thing squared. Notice 3 times 3 is 9, 2y times 2y is 4y squared. I mean, we could most definitely write this as 3 squared plus 2y, the whole thing squared, but that's not over on this list. A sum of squares doesn't factor nicely. It's because of complex numbers and stuff. Okay, so that means what we can do is apply this formula again to this part where we have a new value of a, which is 3, and a new value of b, which is 2y. So let's see what that gives us. That's going to give us 3 minus 2y, 3 plus 2y, and then 9 plus 4y squared. So that would be like the total factorization of this. So notice it was a 2-step process. Okay. So let's maybe do a couple more, two or three more. So I guess maybe the moral of the story is, you know, sometimes we'll have to apply this kind of thing more than once. And also, if you square something that's squared, you get something to the 4th power. So there could be hidden things that look like squares or cubes. Okay. Okay, so maybe this one next. So w to the 4th z minus wz to the 4th. Okay, so the first thing, which I should have said this in the last example, but we didn't really need it. The first thing is to try to find a common divisor and take out a greatest common factor first. Last time there wasn't a greatest common factor, but this time there is. Notice that we can factor a w and a z out of each of these terms. Because here we have w to the 4, z to the 1. Here we have w to the 1, z to the 4. So in the end, we can factor out a single w and a single z from each of these. So let's see what we get if we do that. So factoring a wz out. So that's going to leave us with a w cubed in this first term minus z cubed in this second term. So let's just go ahead and check to make sure that we did not change anything. So if we distribute wz onto w cubed, well, we're going to get w to the 4th using exponent rules. And then likewise, if we distribute it onto the z cubed, we're going to get that. So by exponent rules again. So we're good to go. We factored correctly. But now we can see that this guy is exactly like our difference of cubes formula down here, where a is equal to w and b is equal to z. So that's nice. So all we have to do is apply that difference of cubes formula. So this is going to give us w times z. So that's the stuff that's out front. And then we have w minus z, and then w squared plus wz plus z squared. And that would be like the final factored form of this. Okay. Okay, let's maybe do 2 more. So I think here's kind of a short one so we can fit it on this same board. Let's maybe do 75 t to the 4th plus 30 t cubed plus 3t squared. Okay, so like before, we want to look for a greatest common factor. So notice t squared will definitely be included in that greatest common factor because all of these terms are multiples of t squared, but all of these terms are also multiples of 3. So we can also factor a 3 out. So that means in the end, we can factor a 3 times t squared out of this whole thing. So let's see what that leaves us with. So 75 divided by 3 is 25. And then t to the 4th divided by t squared is going to be t squared. 30 divided by 3 is 10. So that's going to be plus 10t. And then 3 divided by 3 is 1. So that's just going to be plus 1. Now we want to look over there and see if that fits any of our common factoring formulas. And it does. Notice that that is going to be equal to this one, where a is equal to 5t and b is equal to 1. And we can check that because if we square 5t, we get 25t squared. If we square 1, we get 1. And then if we do the 2 times 5t times 1, we're going to get 10t. So that works out. So in other words, we can write this as 3t squared and then 5t plus 1, the whole thing squared. So we factored it completely. Okay, so let's maybe do one more of these. And then we'll move on to more general factoring type formulas. So maybe the last one will be a little bit juicier. So let's do maybe x to the 6 minus 64. So you may look at this and say, oh, I've got a 6th power there, but there are no 6th powers over here in our list of common factoring formulas, but that's okay, because I know by exponent rules, a 6th power can also be viewed as a 3rd power and as a 2nd power. Let's maybe go ahead and write that over here. So let's maybe notice that x to the 6th is equal to x squared, the whole thing cubed. Again, that's by exponent rules because 3 times 2 is 6, but it's also equal to x cubed, the whole thing squared. For the same reason, because x cubed squared, that's going to be x to the 3 times 2, which is x to the 6. So that means we could potentially use either of these, this difference of cubes or the difference of squares. And you can actually do this both ways and you get the same answer. So maybe let's use the difference of squares. I think it's a little bit easier. So what I want to do is first rewrite this as x cubed, the whole thing squared, minus. Now I want to think about 64 as something squared, but 64 is 8 squared. So in other words, I'm using this difference of squares formula with a equals x cubed and b equals 8. So that's how I'm applying that difference of squares formula. So let's see what that gives us. That's going to give us x cubed minus 8 and then x cubed plus 8 by applying that directly. Okay, now we look at each of these and see if we can go any further down. So we've got some common factoring formulas that involve cubes. We've got 2 of them, one for sums and one for differences. We just have to answer the question, is 8 a perfect cube? And it is. 8 is equal to 2 cubed. So maybe we could rewrite this as x cubed plus 2 cubed, and then x cubed, sorry, the first one should have been minus 2 cubed. And now we can apply each of these kind of separately, where a is equal to x and b is equal to 2. So a equals x, b equals 2. And we're going to do that to each of these. So we're going to do the a cubed minus b cubed to this one, the a cubed plus b cubed to that one. So let's see what we get. We're going to get x minus 2. And then x squared plus 2x plus 4. So let's make sure that's right. So that's like a minus b, a squared plus ab plus b squared. So that works out. So let's maybe just point out that that is the factorization of this term. And then the factorization of this next term is x plus 2, and then x squared minus 2x plus 4. Again, like applying that formula over there for the sum of 2 cubes. And so this one factors into that. And so now that's a complete factorization. You might try to think about factoring these leftover quadratics, but it essentially won't work. And we'll kind of see why it doesn't work when we talk about more general factoring in just a second. Okay, so that's essentially the name of the game when it comes to common factoring formulas. Sometimes you'll have to tweak the setup of your problem so that it fits one of those, either by interpreting like even powers as squares or something like that. Okay, good. So now the next thing that I want to do is talk about more factoring strategies other than just having the common factoring formulas. And the good news here is that if you forget the common factoring formulas, you can always just use a general factoring strategy instead. Okay, so let's maybe head this more factoring. Good. So let's see. Maybe the first one is going to be grouping. So this is by far less common, but still important to keep in mind. And this is set up for the following situation. So let's say if the expression that you're trying to factor contains 4 terms, this can obviously like be expanded to have like more than 4 terms, but in general, we'll have 4 terms and no common factor. So we saw like how to take out a common factor. Well, what if there is no common factor? Well, sometimes you can still factor it out into a product of binomials if you're lucky. So let's like look at the standard example. So that would be like AC plus BC plus AD plus BD. So the idea is that there's no common factor for all 4 seen as a group, but if you look at them as pairs, there are common factors. So notice the common factor of the first 2 terms is C. The common factor of the second 2 terms is D. So that means we can think about grouping the first 2 and the second 2 and then factoring out. So this will give us A plus B times C. So that's what's going on with this first term. And then we can do something like that here too. So we'll have A plus B times D. So that's what we get from factoring out this second bit. But now the big leap here is you want to consider this A plus B term as being a single object. But if you consider this A plus B term as being a single object, you can factor that out of the entire thing. And that'll leave us with A plus B. If we factor it out of this first term, we get C. If we factor it out of the second, we get D. So we get A plus B times C plus D. And now notice if you were to FOIL this out, you would get back to this original. So like I said, this is important to remember, but it's not going to occur super often. Much more commonly will be like unfoiling. In other words, you start with a trinomial, that's a polynomial with 3 terms, and you rip it apart into 2 binomials. So let's maybe write that down. So unfoiling. It's like not really a graceful terminology, but that's what we'll write down. So given a polynomial ax squared plus bx plus c, where I'm using capital letters for each of those, you want to find, and generally this is by guess and check. And yeah, there's like an algorithm where you don't have to guess and check, but it's like way slower. I think guessing and checking is really a lot better here. And we'll go over a bunch of examples so it won't seem so daunting. You guess and check until you have the following factorization. So ax squared plus bx plus c is going to factor like little ax plus b times little cx plus d. So it's like doing the foiling in reverse. Okay, so let's do some examples. So x squared minus x minus 6. So the trick goes like this. You want to factor this in a way so that when you FOIL it out, you get a -6 here and a -1 there. So given that we've got an x squared as the leading term, we kind of know that this needs to factor as x and x. So we can already say that. Because x times x is x squared, there's not going to be a coefficient on the x. And then next, given the fact that you have a minus sign here, that tells us that one of these should be plus something and one of these should be minus something. Notice if they were both pluses, you would get a plus. If they were both minuses, you would also get a plus because a negative times a negative is a positive. So that means they have to have opposite signs. So now we just have to determine what numbers go here. And so those numbers should satisfy the following rule. So when we multiply them, we get 6. And then when we add them, we get -1. So why is that? Well, that's because when you FOIL it out, the constant term is their product, but the coefficient of x is their sum. So let's see, how could you get a product of -6 and a sum of -1? Well, you could have +2 minus 3. Now let's go ahead and check to make sure that works just by FOILing it out. So we've got x plus 2 times x minus 3. So if we FOIL that out, so the x multiplies the x, the 2 multiplies the -3, and then like that. So that's going to give us x squared minus 3x plus 2x minus 6. So now after combining like terms, we get x squared minus x minus 6, which is exactly what we wanted to get. So it worked. So this idea of these two numbers adding to the coefficient of x and multiplying to the constant term, that's like the biggest takeaway here. Okay, let's maybe look at another example. Maybe x squared minus 8x plus 15. Okay, so what are we going to get there? So let's see. We know that this is going to look like x something, and that's because we've got an x squared here. And then next, we know that we need 2 minuses here. So why do we know there are 2 minuses there? Well, we've got a plus sign here and a minus sign here. So notice if we have 2 minuses, product of 2 negative numbers is positive, but the sum of 2 negative numbers is negative. So now we want to think, what 2 numbers can we multiply together to get 15 and add together to get -8? But we see, hopefully quickly, that that's like 5 and 3. So we've got x minus 5, x minus 3. And now we could check this just the same way. So notice we could FOIL it out. We'll get x squared minus 5x minus 3x plus 15. So that -5 times the -3 gives you that plus 15. And so in the end, this will achieve the correct factorization. Okay, so let's look at another one. So let's say this maybe 2y squared minus 11y plus 5. So a little bit trickier here because we've got a 2y squared instead of just a y squared. But we can still suitably guess and check until we get the answer, I think. So let's try it. So we know, since we have a 2y squared, well, 2 can only factor in one way. It can factor as 2 times 1. So that is actually pretty lucky. So we know that one of these terms is going to start with a 2y, and the second term is going to start with a y. Then we've got a positive number here and a negative number here. So that tells us both of these have to be negative. And that's because a negative times a negative is a positive, but a negative plus a negative is a negative. And then next, we know that the only way that 5 can factor is 1 times 5. That's because it's prime, which means we have two choices. We could put a 1 or a 5 here, or we could put a 1 or a 5 here. And we just have to play around with each one and see which one works. So let's maybe put a 5 here and a 1 here, and notice that that is going to work. So if we multiply this out, so check, we do 2y minus 1, y minus 5. So let's go ahead and FOIL that out. So 2y times y, and then negative 1 times negative 5, and then those like that. So that's going to give us 2y squared minus 10y minus y plus 5. But now combining like terms, that gives us 2y squared minus 11y plus 5, which is exactly what we needed. And then I'll let you guys check, well, what happens if you make this other choice, a 5 here and a 1 there? And what you'll see is that this middle coefficient will not be correct. So if you put a 5 here, you're going to have 5y, a 1 here, you'll have 2y. So you're going to have something like negative 7y instead of negative 11, so it doesn't give you the right factorization. Okay, let's do a couple more. So let's do one where you group and factor, and then we'll do a couple where you guys try them, and then we'll look at the solution. So the group and factor, let's say this, 2t cubed minus 10t squared plus 3t minus 15. Okay, so if we look at this, there are 4 total terms, and there's no greatest common factor among the terms. So the only strategy that we have now is this grouping. So maybe we can group them into 2 pairs, and there will be a greatest common factor among the pairs. So let's see, if we group it like that, so this orange pair, that has a greatest common factor, and that greatest common factor is 2t squared. So notice if we take a 2t squared out of this, what are we left with? So we're going to be left with t minus 5. So let's just go ahead and check that. So 2t squared times t is 2t cubed. 2t squared times negative 5 is negative 10t squared, because 2 times 5 is 10. Good. Now let's see, can we take a greatest common factor out of this next bit? We can, and it'll be 3. And then we're left with t minus 5. So that's what we get from factoring out here. Okay, now the next thing is we want to think about this t minus 5 as being one term all on its own, and we can factor that out of the whole thing. So we factor a t minus 5 out, and let's see what we're left with. If we divide a t minus 5 out of the first term, all we're left with is 2t squared. And if we factor a t minus 5 out of the last term, all we're left with is a plus 3. So we end up with that factorization. And now we look at that and think, is there anything else I can do? And in this case, there is nothing else we can do. because this doesn't have one of the standard forms that we talked about before. So we're all set. Okay, good. So let's maybe try this one. I'll give you guys like 2 or 3 minutes to try this, and then we'll go over it, and we'll do this maybe once or twice. So let's say this, 20x cubed minus 7x squared minus 6x. So hint, you're gonna have to take your greatest common factor out first. Okay, so like I said, I'll give you guys a few minutes to try that, and then we'll go over it. So let's maybe go ahead and look at this one. So like I said before, we should probably take out a greatest common factor. The hint is that there is an x, which is a term from all of these. And, well, that's all there is. Notice that the greatest common factor of the numbers is just 1. So we can't take anything else out other than just an x. So let's maybe go ahead and do that. So this is going to be x times 20x squared minus 7x minus 6. Good. Now, I'm actually going to like move this up to the top so we have a little bit more room. So let's see, we've got 20x cubed minus 7x squared minus 6x. So we factored a greatest common factor of just x out. That leaves us with 20x squared minus 7x minus 6. Good. And now this is a game of guessing and checking. So you want to think about all the different ways that you can take a product to get 20 and all of the different ways you can take a product to get 6. So maybe we could keep a list over here and notice that 20 is equal to 1 times 20. It's also equal to 2 times 10 and 4 times 5. So those are the 3 ways to take a product of 2 numbers to get 20. And then 6 is equal to, well, 1 times 6 and 2 times 3. So those are like all of our choices. So if we were to factor this into 2 parts, so we've got x and then something, something, we know that one of these parts will come from one of these factors of 20 over here, and the other part will come from one of these factors of 6. So since 7 is kind of a small-ish number, I would say you probably want to try something in the middle first. So let's maybe try this 4 times 5. So that means we would have a 4x here and a 5x here. And then we just need to play with it to see if we can make this work. So let's see what our choices are. We could have a -1 and a +6. We could have a +1 and a -6. We could have a -2 and a +3, or we could have a +2 and a -3. And let's see, do any of those work? So let's see, 4 times 3 is 12. Yeah, so none of those are going to work. So now we play with, or vice versa, I should say, or we could like switch these over. And I think switching these over is going to give us one that works. So notice if we have, so again, by guessing and checking, just by trying each of these, we'll have x, 4x, 5x. And then maybe if we have a 3 here, no, and a 2 here, no, that's not going to work. Oh, sorry, maybe a 2 here and a 3 here. So is that going to work? So notice 2 times 3 is 6. 3 times 5 is 15. 2 times 4 is 8. Oh, but like 15 minus 8 is 7. So we're good to go. Now we just have to choose the correct sign. So this one's going to be a negative and this one's going to be a positive. And that's because we need the 15 to be negative because we've got a -7x up here. So I know it's like it feels a little random to just guess and check these types of numbers until it all works out, but it's really the best way to do it. And after practicing these kind of factorizations for maybe like half a dozen or a dozen of them, it comes together pretty quickly. Okay, so we have like 3 minutes left. Let's maybe do one more, and then we'll call it. So let's look at this maybe. 36 minus 11z minus 12z squared. So we want to think about the same kind of factorization chart. So 36 can be 36 times 1, maybe like 1 times 36, or it could be 2 times 18, or it could be 3 times 12, or it could be 4 times 9. And I think those are all the choices up to permutation. And then 12 can be 1 times 12, or 2 times 6, or 3 times 4. So that means when we split this up into binomials, we're going to have parts from this list of choices and then parts from this list of choices. So let's see what we have. So let's just maybe try 3 and 12 first. So let's say we have a 3 here and a 12 here. Now we're going to have something times z here and something times z here. And one of them is going to be positive and one of them is going to be negative. And we have to choose them so they multiply to 12. In other words, we've got these choices 1, 12, 2 and 6, or 3 and 4. So do any of those work? So let's see. So this one is not going to work. So let's see, 2 and 6. So if we put a 2 here and a 6 here, well, 2 times 3 is 6. 6 times 12 is like 72. That's never going to get us to negative 11. So what if we put 1 and 12? So a 1 here and a 12 here, that's not going to work. A 12 here and a 1 here is also not going to work. Well, let's maybe try this 2 and 6 in reverse. So if we put a 2 here and a 6 here, so 2 times 12 is 24, 6 times 3 is 18, but that's not going to add up to negative 11. So it looks like this choice of a 3 here and a 12 here will not work. So we've ruled out this 3 and 12. So let's maybe try 4 and 9. So we ruled that out. So if we do 4 something times z and then 9 something times z. Let's see if we can make that work with these two parts right here. So if we put a 1 here and a 12 here, that's not going to work because 12 times 9 is way too big. If we put a 12 here and a 1 here, well, that's still not going to work because 4 times 12 is way too big. So we just have to move down the line. So we can't use this 1 times 12. Maybe we can use this 2 times 6. So let's see. No, that's not going to work because notice we get two things that are both even here. But an even number can never add up to an odd number, which is 11. So maybe we take 3 and 12. So what if we put a 3 here? Sorry, 3 and 4 and a 4 here. So that's our only choice in order to get an odd number. So 4 times 4 is 16. 3 times 9 is 27. That's going to work. So let's notice that 27 minus 16 is 11. So that means I need the 27 to be negative because I have negative 11 there. So I can make this negative and this positive.